Hello and welcome to your background video for copper amine synthesis and UV spectroscopic analysis. In this laboratory, we will be preparing a complex ion by adding ammonia to a copper solution. The resulting compound is an intense blue color. Lots of transition metal complexes can produce interesting colored compounds, and chemists tend to think that they are cool, so you should too. Additionally, we will be using spectrophotometry to analyze the solutions that you will prepare. Your task will be to establish the relationship between the concentration of the copper complex and its absorbance as measured by the spectrophotometer. To establish the concentration versus absorbance relationship, we will use our dilution techniques to prepare a series of solutions that vary the concentration. Instead of the direct dilution performed in the physical properties lab, you will be learning how to perform what is referred to as a serial dilution. A serial dilution uses a pipette and a volumetric flask, as we did earlier in the semester, but allows us to change the concentration by a factor of 10 for each subsequent sample. We have discussed concentration by weight in other labs, but a more useful way to measure concentration is by how many atoms or molecules of solute are in a given volume of solution. Now, this poses a bit of a problem, because even just a few salt crystals contain an amazing number of individual atoms, and it would be quite tedious to say that you have 38,538,265,940,382 atoms per liter. So we use a unit of measurement called the mole. 1 mole represents 6.022 times 10 to the 23rd atoms, in the same way that, for example, 1 dozen represents 12 of something. Using the mole and moles per liter, or molarity, we can report concentrations in amounts that are easier to work with, such as 1 molar or 0.4 molar. In this lab, you will be preparing a 0.02 molar solution from a solid, so you will need to perform some calculations to figure out how much solid you will need to achieve the desired concentration. Because it is unlikely you will have seen this calculation in the lecture, you need to pay close attention to this sample calculation and review similar calculations in your textbook. Let's say we need to prepare a 0.1 molar solution of sodium chloride. We have a 50 ml volumetric flask and some solid sodium chloride. We need to figure out how many grams of sodium chloride need to be put into the flask to end up with 50 milliliters of a 0.1 molar solution. You will start with the molarity, which has the units of moles per liter. The first step is to determine the number of moles of sodium chloride that would be required in the 50 milliliter flask to make the 0.1 molar solution. We will first convert milliliters to liters, then multiply the molarity by the volume to get moles. Now we know that we need to put 0.005 moles of sodium chloride into the flask. However, we can't measure out 0.005 moles of sodium chloride because our balance measures in grams. To convert moles to grams, you'll have to determine the molar mass by using the values from the periodic table. The molar mass represents how many grams of the substance would be observed if you had 1 mole. Adding the atomic masses of each element in the compound together will give us the molar mass, so it'll be 23 grams per mole for the sodium and 35.5 grams per mole for the chloride. That makes our molar mass 58.5 grams per mole. To get to grams, we can multiply this molar mass by the moles, so 58.5 times 0.005 equals 0.2925 grams. We now need to know that we will need to put 0.2925 grams of sodium chloride into the flask to make 50 milliliters of 0.1 molar sodium chloride solution. In practice, you don't need to get exactly 0.2925 grams of sodium chloride. You should measure a mass very close to that and redo the calculation to report an accurate concentration. Once we have our calculated concentration for our stock solution, we will use the same M1V1, M2V2 relationship we used in the density lab to determine the concentration of each new solution prepared in our serial dilution. Your spectrophotometer is actually a super expensive light bulb with a detector. The light bulb emits a known amount of light as measured based on the wattage of the bulb. Some of the light is absorbed by the solute molecules. What light isn't absorbed passes through the solvent to the detector. The detector then measures the fraction of the light that reaches it. The spectrophotometer reports the percentage of light that was absorbed by the solution. After this lab, you should be able to describe how increasing the concentration, which means increasing the number of solute particles, is related to the absorbance of the light. Is it linear, inverse, logarithmic, or exponential? You'll plot the data to find out. This approach is identical to some of our earlier labs. If you think back to the physical properties lab, we made some dilutions, calculated the concentrations, and then measured the density of each solution. Using our data, we created a graph that allowed us to determine the relationship between the two variables. If you were given a sugar solution with an unknown concentration, you could measure the density, then use the relationship that you determined to find the concentration. The same principles apply here. You made your dilutions, you measured a physical property of your dilutions, and now you will need to graph them to find the relationship between them, whether it is linear, inverse, logarithmic, or even if there is a relationship at all. Thank you for watching. Please go watch the technique video now.